Hello, my name is Brandon Montemiro. I'm a postdoc here at the University of Washington, and I will be talking about the SubZero sea ice model. I'll be focusing on validation and test cases of the model. So our first study will be looking at the Nares Strait. The Nares Strait is a waterway between Greenland and Canada, and this location was chosen because there are a number of satellite observations from this region, which will allow us to validate our model. We can look at things such as the mass transport through the region, as well as the features that are observed in the sea ice upon breakup, such as the arch formation. Now, for our model, the boundaries will be shown as two green flows, and these are both immovable and unbreakable, which will allow our sea ice to interact with. The simulation is limited to only collisions and fractures of sea ice. This is because we're looking at spring and summertime conditions. The flow model is initialized with sea ice completely packed to 100% at the top of the domain. It'll break up and move through the channel, and it'll be pushed through by winds and oceans from top to bottom. And when certain flows fracture and reach a certain lower threshold on their flow size, they will be removed from the simulation. In future simulations, we would look to see what happens if we retain these flows in the model, but allow them to not fracture anymore. So shown on the left, we are looking at NASA Worldview from 2019. We can see the ice pack break up and move through the channel, and we can see at times the flow is on the left-hand side of the channel. On the right-hand side, we have our model. As stated before, the boundaries are these green flows, and they are not able to move or fracture. And up top in the gray, we have our flows. They'll turn pink, and the shading is indicative of the stress. With the pinker the flow, the higher the stress it is experiencing. We also have these arrows showing the sea ice velocity that is homogenized. We can see flows that get stuck in the domain, similar to what we see in the observational data. They move through the channel. Certain flows will find their way into these side channels and just move down through. Our next test case that we want to look at is a winter test case. In this situation, we have fractures, we have ridging, we have welding, we create new flows in the open space, and we are running this with doubly periodic boundary conditions. The forcing in this scenario comes from quad gyre, as well as uniform winds blowing from the bottom left to the top right. And we can see that we have a qualitative agreement with this SAR image up here, where we have some of the large flows, and then we have the thin new ice in between these larger flows. Looking at some of the data from the output from the simulation, we can look at the number of flows. We can see there's an initial drop-off when things start welding in the beginning, and then when the stress reaches a high enough level, they start to break up, as well as we have these new flows that are being created in the open region, and we can see we have a continuous increase in the volume of sea ice. We can also look at the flow size distribution. So plotted here on the left, we have the initial and the final states from the video. And we can see we start to reach this more evenly distributed flow size, and we can look at the power law exponent, and we can see that we steady off around this minus 1.5 value for the power law exponent. And this is in complete agreement with the Stern et al. Paper, who have collected a number of flow size distributions from various observational studies. The next phenomenon that we want to look at with our model is inertial oscillations. Inertial oscillations are caused by time-varying winds depositing momentum into the ice ocean system. So these are observed in ice buoys, often which exhibit circular motions overexposed on the overall unidirectional motion. And so shown here on the left is from Gimbert et al. We can see in the red boxes these circular motions. And on the right side of the figure, what we have here is the Fourier spectrum of the velocity of the buoy. And we can see a number of different peaks in this buoy. We have the 0, which is your mean drift value. We have the plus and minus 2, which correspond with the components of the velocity with the tides. And we have this minus 1.35, which corresponds to the Coriolis frequency. And for the model with these inertial oscillations, what we want to look at is the impact of the flow interactions on the oscillation amplitude. And so since we are looking to explore the flow interactions, we don't want to try to model the oceanic response because this is a bit tricky and will slow down our computations. So what we're going to do is we're going to prescribe the ocean velocity. And we're going to do that with the equation shown here, where we have a fixed amplitude u, as well as a fixed inertial frequency f, which is the Coriolis frequency. And so when we run the model, we are only going to include collisions and interactions with the flows and the outer stationary sea ice, which is represented by the boundary. And in this case, the boundary that we're going to run with is a circular boundary. And this is due to the isotropy of the forcing in the sea ice mode. And lastly, we're going to run the simulation over a number of different sea ice concentrations. All right, so here we're looking at two different runs with the flows initialized at a 25% concentration and at a 90% concentration. And in the top right, we are able to look at the velocity of the sea ice compared to the velocity of the ocean at that time. So the ocean velocity is shown in red, the ice velocity is shown in black, and we can see here from these plots that we have vastly different amplitudes of our sea ice for these two different situations based on the sea ice concentration. And so when we run this for a whole different number of initial concentrations, we can see that the sea ice amplitude decreases dramatically with the increasing in sea ice. And that there is a critical concentration of somewhere in the 70 to 80% range, where once we reach that, the amplitude dramatically drops off. And the difference between the ice and the ocean velocity magnitude and their positive correlation implies that the sea ice is receiving the kinetic energy and that the energy is being dissipated frictionally due to interactions between the ice flows. The last test case we want to look at is trying to super parameterize the sea ice, and we are calling this the SPICE model. And this is a framework for modeling sea ice utilizing a combination of solving macroscale equations and a microscale DEM. And so at the macro scale, we're going to solve a system of PDEs, and it is at this scale that we will include the sea ice coupling and forcing due to the atmosphere and the ocean. And then the flow scale, we're going to use the SubZero model to resolve flow-flow interactions. And this will be forced with changing the boundaries with inputs from this large-scale model, and we also take inputs on the concentration of the sea ice. To start off, we're going to have a simple one-way coupling. So what we're looking at here is the full model, and we are trying to just blow from left, have winds blowing from left to right. We're going to keep it at 100% concentration, and we shall see that we have higher stress on the right, where again, the color is indicative of the stress of the flows. And we can also see that there's a wave propagating from back and forth when it is interacting with the boundaries. And so what we're going to do is we're going to take a number of the subdomains on this of this size. We're going to take the homogenized sea ice velocity values and use those velocities to augment the boundaries of this domain. And we are going to then get the stress from this, because it is the divergence to the stress tensor that we will ultimately feed back into the large scale PDEs that we will solve in the SPICE model. And so we do this. So we split up the domain in one dimension. We run this small scale models with the inputs from the large scale full model, and we get the stress, and we wanted to compare the stress from the truth with the stress from the SPICE model. And we can see that in general, there is a qualitative agreement, and it is pretty good at the beginning. And we can look at it as a Hav-Muller plot, and we can see at the beginning, we have very good agreement. And overall, we can see this wave propagating back and forth in both models, and we have a general qualitative agreement between the two models. So in summary, We are able to reproduce the springtime flows moving through the Nares Strait. In the winter test case, we were able to reproduce the observed flow size distribution. When it comes to the inertial oscillations, we were able to show that the CS amplitude decreases dramatically with increased concentration. And we also have some agreement between the stress output for the full SubZero model and the one-way coupled SPICE model. Thank you.